start with the introduction. So our next speaker in this afternoon slot, which will encompass a late morning slot, which will encompass actually 6 presentations. The first of them is Marcin Gregorczyk from Warsaw University of Technology, and he will talk about the security solution, security framework that was created for the purpose of the IoRL project. It's an SDN-NFV based or any SDN-NFV solution for IoRL. And I think, Marcin, you can start, as it is now 11:15, and we have a very busy agenda. Marcin, please start.
Okay, thank you very much. My name is Marcin Gregorczyk again. I would like to welcome everybody, and I would like to present a contribution of Warsaw University of Technology to IoRL project. I will talk about integrated security framework. This is our tool that was created especially for IoRL project. Integrated security framework consists 2 basic elements, the backend and the frontend. Backend is SDN REU controller, which monitors traffic going through the Open vSwitch technology. It can interact with malicious traffic. So if SDN REU controller by the mean of the any created module will report that something is someone is doing something nasty, it will create automatically ban to avoid such traffic going through the system. So this is the backend. This is the heart of our solution. The frontend is security web dashboard, where administrator can view what is going on in the system. It can enable, disable modules. It can alter the configuration in the real time. What is worth mentioning that our solution is designed and implemented in modular way. So if we'll come up with another module, it is very easy to integrate with rest of our solution. Additionally, we integrated with IoRL location service. So if our module will report that someone is doing something nasty by connecting to IoRL location database and querying it, if the database provides such information, we can say, okay, so this device is doing something nasty and it is located over here. Okay, so we created security modules for to mitigate common attacks, and they can be divided in 3 basic groups. The first one is rogue transmitter, so TCP SYN port scan. The second one is denial of service, and the third one is eavesdropping. So we have modules for each of this group. In case of this denial of service, we have DHCP server address pool exhaustion, and in case of eavesdropping, we have a module for finding if someone is doing sniffing. Additionally, we have 2 very simple modules related to IP address spoofing. And as well, during 6 months extension of our project, we created new modules. One of them is, sorry, I hear some background noise. Could you please mute yourself? Was it only me?
As far as I can tell, everybody was muted. But what I can also say, Marcin, that there is something overlaid on your screen, so we don't see. Actually, it's not even in the presenter mode, and there is also a screen. Yes, now we can see your screen, but yeah, put it in the full screen mode, presenter mode. Yes.
Okay.
But not everyone is muted. Hongfar and Carol, Honfoga and Israel and Yui are not muted.
Okay, let's move on, guys. We created additional modules during 6 months extension. The first one is a generic firewall, which can be used to filter any type of traffic, not only the malicious one. We can create filtering rules for any type of traffic. The second one is DOS attacks against SDN controller, as SDN provides core networking functions in 5G. It also introduces new elements that can be targeted to the hackers. And also we integrated with Suricata intrusion detection system. This is the architecture of our solution. In here you can see that there is a RIU controller which connects using OpenFlow protocol to OVS bridges, so we can instruct every bridge on the system to filter traffic, to do the further exploitation by our security modules. So we can check what is going on with UE devices, with VLC devices, etc., etc. This is the main screen of the dashboard. So in the first tab, we can see that someone is doing something that was fallen into our security module. If we are able to reach location service, we can show the location of this malicious device. On the second tab, you can see that modules have their own configuration. We can stop and start modules independently and alter the configuration in the real time. Every module is described here with their parameters. So if someone will log into to our security to our dashboard, it can check what is going on and alter the configuration if something has to be redefined. On the logs tab, you can see that there are logs displayed with the timestamp of the specific event, the IP address and MAC address of a device that was considered to be malicious, and it was already banned. On the other hand, it is only a software. We might create bugs in our software. So if something will go wrong, you can revoke all of the bans. You can restart the controller or clear OpenFlow rules. So it will help to debug what is going on the system if our security modules are not working as designed. On the bans tab, you can see that there are system bans, which means that these are bans created automatically by the security modules. And user bans are the firewall functionality, so we can filter any type of traffic based on MAC address, IP address, or transport layer port. Last but not least, Suricata, so well-known open source intrusion detection system. In here, we can see that Suricata is reporting a lot of traffic that is suspected to be malicious. This is extension to our security modules. Our security modules work on specific issue. Suricata, because it has wide open community support, it provides more and more information on the network security. And if Suricata will suspect that some kind of traffic is malicious, we can immediately, by doing only 2 clicks of the mouse, create ban for such traffic. In here, you have screen of a scene in a Matrix Reloaded movie. In this scene, one of the main characters, Trinity, is trying to hack to the nuclear plant, and she is using Nmap tool. I wanted to show this picture because Nmap is a real hacker tool that provides information on open services. And if one of our modules tries to address this security issue, so if our security module is disabled, you can see that scanning was done in less than a second, and a lot of open ports are presented to the attacker. These open ports can be used to perform further exploitation. But if we will enable our module, exactly the same activity will take almost 1 hour, and no open ports are reported. Additionally, we can see that this activity was tracked by our security modules. We published 2 papers regarding this security module. So if someone is interested in details, please go ahead. These are in open access, so you can read them and see what is going on inside of our security module. Second security module, DHCP starvation. So DHCP is one of the most common network services. If attacker will exhaust pool of available IP addresses and users cannot connect to the network, so it can be very annoying, but also very dangerous because network cannot work as designed. So this is type of denial of service attacks. So we created algorithm developed specially for IoRL project to countermeasure this security threat. Also, we published another paper. So if you are interested, you can reach it. The third module is regarding eavesdropping. We are trying to discover if someone is sniffing the network traffic. We propose 2 methods. One of them is utilizing machine learning, so artificial intelligence. Also, we created 2 very good papers that were published using open access. And we have those simple modules regarding filtering of IP addresses, source addresses, and ARP requests. These are like engineering solutions, so they are work on. There are not many research that we can do with those modules, but they simply work. During our 6-month extension, as I told before, we introduced extra modules. First one is the firewall, so we can create filtering rules based on the MAC address, IP address, and ports. So we don't need any specific extra tool, extra device for IoRL to create a firewall. We can use our security module. Additionally, Suricata, as I said before, a well-known open source intrusion detection system. We integrated we integrated Suricata with our dashboard. So if Suricata reports any malicious traffic, it can be easily banned using our dashboard with only 2 clicks. Last but not least, as we are focusing on SDN, which is called cloud computing, modern data centers networking. It has many advantages, but also provides new elements that can be exploited. One of them is a DOS attack on controller of SDN network. So we created another module for countermeasuring this type of attacks. As a summary, Warsaw University of Technology provided required security modules for our project. Everything that was agreed was provided. We also created a new additional modules during extension, and we are integrating with IoRL allocation service to integrate more deeply with IoRL project. Okay, and that's all from my side. If you have any questions, I'm happy to answer them right now or via email or in the chat. Thank you very much for your attention.
Thank you very much, Marcin. I think that was very good. Again, you really kept to the time, which means that we have time for 1 or maybe 2 questions. I haven't seen anything on the chat channel. But yeah, I mean, if there is any question regarding the security framework.
Yeah, you are free to reach me via email later on. That's not a problem.
Yeah, or we try to answer things in the chat channel as you know. I mean, if it takes time for you to formulate your question. I mean, if this is the case, then maybe we should really move on. And we can come back, I mean, no problem. So the next one is Matthias Elasso. I hope I pronounced your name correctly, from JOADA, who will talk to us about the multi-source streaming. Matthias, yeah, you are ready. Thank you very much.
Oh, yes. Can you hear me? Hello. Can you hear me?
Certainly.
Okay, sorry, I had some issues with my microphone. Okay, so thank you very much. So my name is Mathias Laco, and I'm a research engineer at JOADA, a small company in France. And I'm going to talk about video streaming solutions to improve the way we can deliver a video through multiple paths. It is especially important in the context of IoRL, where we may have several network paths available to deliver the video data. And it may be important to have specific solutions and algorithms to select the appropriate path at the appropriate time. So, oh, I cannot control, oh, okay. So, well, the way people consume video content have evolved during the last year because of course, when I was younger, video delivery was mainly dominated by television channels, but now video data are transferred through the internet. And for example, it can be transferred through the internet of Radiolite project. The Cisco have studied the rise of video streaming through the internet, and right now the video data represents no less than 70% of all of the data circulating on the internet. So video streaming is an important topic when we talk about transferring video data. This number is even expected to reach like 82% by 2022. Of course, because, for example, in IoRL and in future networks in general, we are going to have faster broadband speeds and also more internet users connected with more devices. That means that we will be able to deliver a lot of content, of video content, and also we will be able to deliver bigger video streams like ultra high definition content or immersive videos. It is worth to note in this context that 17% of video streams are expected to be live streams. To be clear about what is a live stream, well, we have the example of a progress bar of a live stream. During a live stream, the video segments are created at the same time the user is watching the video, of course. So this is what the video progress bar looks like. You have the playback positions, meaning the video data that are being watched by the user. We have the real life positions, which means the frame that is being captured by a camera, for example. And between the two, we have an important metric for live streaming, which is the live delay. Of course, for live streaming, we want to reduce the live delay to a minimum. In gray, we have what we call the buffer in video streaming. It's the quantity of data that we have already received in advance. This buffer is very important for video on demand streaming because thanks to this buffer, we are able to manage the specific case where we have a network loss. For example, we have some packet loss, unexpected packet loss. Well, thanks to this buffer, we are able to display the video to the user during a certain amount of time. However, for live streams, we cannot do a lot of things with the buffer because we want to minimize this buffer to a minimum in order to have a minimized live delay. The previous speakers have already presented the challenges of IoRL. So for the point of view of video delivery, we can consider a very simplified point of view of the IoRL architecture. Meaning that we have several connections, several networks connections between the user and the system. So of course, we can receive data through the visible light and millimeter wave, as it has been explained before. But it is also possible to be connected at the same time using other existing or state-of-the-art technologies, such as 4G, Wi-Fi, or maybe other kind of Wi-Fi technology, and all of that connected to the same global system, for example. So what is the problem with this scenario? It's because the technology of the project are delivering live streams with a low delay can be difficult, because if a user, like in figure 1, is standing behind the light, just like that, it will have a very important bandwidth and also a very small delay. So it should work well to deliver a very high quality video content. However, if he moves outside of the range of the light, he might be in a dark zone, according to the situation of the room, for example, and he can experience a low download bandwidth with a lot of packet loss. First solutions to solve this kind of issues will be to simply switch from one network to another. It can be done, for example, by monitoring the packet loss to detect when a user is out of range and switch. But it raises some questions, and it may not be optimal for every scenario of a live stream, because according to the selected threshold to detect the packet loss, the system may need a few seconds to detect that a network modification is needed. And in this situation, the live stream may be interrupted. Moreover, we are not able to take advantage of the plurality of network by aggregating the bandwidth available on every path. To answer all of those issues, we propose the multiple source streaming over remote radio light head, or I will call it MSS in the next slide to be faster. The main idea is that the video client is going to download video data from multiple paths at the same time. So if we have A megabit per second over the light network and B megabit per second on other network, we want to be able to aggregate the bandwidth and receive the sum of A plus B megabit per second. To do that, we are going to download a percentage of high quality from every path. For example, 60% of high quality from the light network and the other 40% of high quality from alternative networks, if we have one available, of course. To do that, we are going to use the main concepts of multiple description codings. One important aspect in our architecture is MSS VNF deployed in the home IP gateway of the project. Video traffic can be redirected to this VNF, and this VNF will be responsible to transcode the video content into several qualities and segment the video data into video segments optimized for the delivery over MSS. To go deeper into the concept of the solutions, I must come back to the main definition of a digital video. So a video is composed of multiple frames displayed at a specific rate, usually between 24 frames per second and 60 frames per second. And the quick succession of pictures is tricking our eyes to see motion. However, storing every single picture will produce very huge files. And if we take a look at these two pictures on my screen, you can see that the only difference is that some circles have moved to another positions. So instead of saving every new frames, we can save some transcoding frames with only some information about the modifications between the two. So a modification of one iframe followed by several encoded frames is called a group of pictures. What is important about the group of pictures is that according to the encoding parameters, they can be independently decoded by the player. So it's a piece of information that we can work on. The concept of MSS is depicted in this slide. So we are going to request some group of pictures in high quality, in dark blue in this example, and some redundant groups in low quality in light blue. According to the download bandwidth observed on every path, the light path and the alternative path, we are going to modify the number of GOP in high quality from every network path, and hence we will be able to have our scenario when we have, for example, 60% of high quality from the light network. So when it works well, we are going to receive all the data, and the player will be able to select the appropriate group of pictures in high quality and display every video frame in high quality. Sometimes we will have some issues and we will not receive all of the data. Well, in these situations, we will be able to display the low quality group of pictures, meaning that the user will have a low quality during a few seconds, but will not experience video interruptions. But when all of the video data are correctly received, what happens with the redundant groups in low quality? Well, the group of pictures are not used, and they are called the overhead, and it's the quantity of data that we downloaded to prevent the interruptions just in case. It may be seen as a drawback of the solutions because it can create network congestion, for example, and we want to avoid that, of course. So in the next slide, we are going to talk about solutions to avoid that. Of course, MSS have been designed for several scenarios, but we are going to focus on live streams. So on live streams, we are not going to be able to make decisions on a lot of group of pictures because we have to reduce the live delay and the buffer. The main questions that we want to answer is it necessary to download a redundant group of pictures? Is it necessary to add this overhead? Well, to answer these questions, we have made some propositions. One of them is for live streaming to evaluate the risk according to previous bandwidth estimations. So if we see, according to the previous recorded bandwidth, that the bandwidth seems to decrease, then a risk is computed. And if the risk is high enough, we are going to ask for redundant GOPs in locality to ensure the reliability of the video streaming sessions. If we make a mistake, well, we will just download a little bit more video data than what is needed, and it's not too bad, obviously. We have evaluated our propositions. So we have developed 3 different players, video players. We have, of course, the first one is MSS, just I have described in the previous slides. And we have also implemented a version of MSS that tries to send redundant low-quality data every time. And we have also studied a state-of-the-art player using the current standardization formats. And we have improved this player by making him able to ping periodically the different network paths available in order to see if it is possible to switch from one network to another. We have made an evaluation in a lab using traces from the project. And the idea is that we studied 2 different scenarios, one where a user is slowly moving under the light, and one where an obstacle is suddenly obstructing the light. We can see here the different network traces obtained from the different video players that I explained before. So we can see that every video player is able to adapt its quality according to the bandwidth observed in the global network. But in red, we can see that the state-of-the-art player may have some trouble sometime when the bandwidth is decreasing, and the user may experience interruptions in their streams. To summarize the evaluations, what we have is that the state-of-the-art player have a lot of rebuffering, which means that it does not have a good reliability, and also a high live latency, but the 2 are related. And our solutions are having, are more reliable and with a lower live latency. In terms of overhead, with our overhead reduction mechanism, we have been able to reduce the overhead of the system from 8% to only 2%, which means that we only have a few frames of overhead in our system. To conclude, well, with these solutions, we were able to increase the quality of the video streaming sessions by aggregating the network resources. We are able to increase the reliability by simultaneously downloading low-quality data from alternative paths. All of that is at the cost of an overhead in the network, but we managed to reduce this overhead to a minimum by using specific algorithms. Of course, we have developed other versions for video on demand streaming and also other algorithms for live streamings, but it was too long to be presented in this presentation, so I focused on the main ideas. Thank you for your attention, and you may ask questions if you want.
Thank you very much, Matthias. Yeah, I mean, again, we are in a good position that we still have a couple of minutes available, but I haven't seen any question to Marcin for the previous talk, and nobody posted anything on the chat channel. So again, I just remind everybody and all the participants all our audience that if you have any questions, we are looking to receive those questions through the chat channel as a primary means. Maybe again, for the sake of time, we move on to the next speaker and the next presentation, and you know, you can take your time formulating your question. We try to take care of it. There is, I think, one pending, but the answer is in the working, so it will come. Okay, so the next talk is the location algorithm and the database, and it's going to be delivered by Alina Shi. She is from ISEP, so from ISSY, and oh, I see another name here now. I mean, maybe she's hiding behind that. I don't know.
Okay, I'm going to share my screen. I'm
Oh,
Lina.
excellent. Thanks. Yeah, we can hear you very well. And please go ahead, Lina.
Okay. Can you see my screen?
I confirm. Well, not now. It was there, but
It's okay now?
not to me.
Wait a moment.
Yes.
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 Okay. Good morning, everyone. I'm Lina from ISEP. Today, I would like to introduce you the 5G visible light communication positioning protocol, location database, and the positioning algorithm in IoRL. Today, my presentation consists of 4 parts. Firstly, I'm going to introduce the background and the motivation, and then I will move on to the VLC-based positioning framework in IoRL. In third part, I will put forward a new method, PSO, to estimate the RSS ranging parameters. Finally, the experimental testbed and results will be detailed. So let's move on to the first part. In recent years, with the emergence of 5G technologies, the convergence of 5G with location-based services are getting more attention than expected, especially in indoor environment. So the 5G white paper pointed out that the 5G network will reliably support the location accuracy better than 1 meter for indoors. With this background, we have investigated the current indoor technologies. As illustrated in this table, you can see that after combining them from VLC and peers, the excellent performance not only in positioning accuracy, but also in cost and power consumption makes VLC stand out. So based on the attractive features of VLC, in our project, we use visible light signals for indoor localization. This slide here illustrates the visible light communication-based positioning framework in IoRL. There are 4 main components, namely the remote radio light hand controller, the location server client, the location database, and the location server. Here, I would like to give you more details about the location database. As you can see here, there are 3 different sets of VLC parameters in the location database. The first one is the mirrored location relevant VLC parameters, which is the received signal strength of the positioning signal. And the second one is the coordinates of all antenna, LED lamps, and also the transmitted power. The last one is the estimated location coordinates of all connected user equipment. In our project, the indoor positioning protocol involves the interaction among the aforementioned four components. The procedure consists of 3 steps. The first step is the measurement of location-relevant parameters. In this step, firstly, the user equipment sends the positioning request to the controller, and then the controller sequentially broadcasts the series of LEDs ID in TDM mode. The user equipment receives the ID from all LEDs in one row, and it will report the LED ID to the location database by using the TCP/IP package. The second step is the location estimation. In this step, the location server first reads the coordinates of the corresponding LED from the location database, and then performs the location algorithm. After that, the location server writes the user equipment's position estimation results to the location database. The last step is the exploitation of location estimation. It means that the location server client provides different location-based services to the user by retrieving the user's position estimation from the location database. In our project, the RSS-based positioning algorithm is adopted to estimate the user location. According to the Lamberton radiation model, the VLC channel gain between the LED and the user equipment can be expressed in this equation. The distance between the LED and the user equipment can be calculated by using the VLC channel gain and the mirrored RSS values. After that, we can get the estimated coordinates of user equipment. But the main issue is it is difficult to obtain the VLC model parameters in the complex indoor environment, and it can further impact on our positioning accuracy. In order to address this issue, we proposed an method named particle swarm optimization to simulate the parameter estimation in a practical indoor environment. Before introduce our method, I would like to give you some brief introduction about PSO. The PSO is an artificial intelligence technique that can be used to find optimization solution, and it has a lot of features such as fast convergence, high search efficiency, and high definition, etc. We would like to use it for the parameter estimation of the VLC channel model in order to improve the positioning accuracy in our project. As you can see here, the PSO method flowchart is detailed in this slide. The PSO inputs are the RSS measurements at different test points and the corresponding distance. The output is the optimized VLC parameter G and M. Then we can use the optimized parameters to modeling a new VLC loss model here for the practical environment. And along with the aforementioned RSS positioning algorithm, we can calculate the coordinates of user equipment and analyze the positioning errors. In order to prove the feasibility, the experimental testbed is built based on the Viavi 5G new radio system. Let's take a look at the figure on the left side. There is the system configuration diagram. the USRP is connected to the system with 10 gigabits internet cable for 5G VLC signal transmission, and the signal will send through the VLC model and the LED lamp and received by a photodiode. The measurements was set up in a particle laboratory environment. As you can see here on the right side, there are 4 commercial LEDs installed on the ceiling to broadcast the 5G visible light communication positioning data. And APD with an optical lens is used to collect the VLC positioning data. Under this experimental environment, there are 30 uniform distributed test points were selected over the 50 centimeters by 50 centimeters positioning area. We calculate the positioning error for the positioning performance evaluation. The positioning error is defined in this equation where x, y, z, and x, e, y, e, z, e are the coordinates of test points and the estimated points respectively. We plotted the distribution of positioning errors in the figure on the left side. As you can see here, the blue sign represents the test points and the red sign represents the estimated points respectively. We selected 30 test points in total, and there are 25 valid points and 5 invalid points. Among these 25 valid test points, the minimum positioning error is 0.55 centimeters, and the maximum positioning error is less than 12 centimeters, and the average error is 12.28 centimeters. Besides that, we also plot the CDF curves of the 25 positioning results in the figure on the right side. As you can see here, it can be found that the current experimental test bed can reach a positioning accuracy of 10 centimeters at the confidence of nearly 81%. That's all. This is my presentation today, and thank you for your attention. Hello?
Sorry, yeah, thanks a lot, Lina.
Okay, thank you.
Yeah, I mean, we noticed that there was a bit of an issue with your voice. I mean, but I hope people could still follow the presentation and understand you. Every time you start.
Sorry, I didn't notice that there is a problem connection.
Yeah, but I think it was, you know, it was still within tolerable limits. Good. Yeah, I mean, again, I don't see any specific question at this point in time.
Okay.
So thanks once again, Lina. So we move on.
Thank you. Thank you.
Yeah.
So I stop sharing my.
Thanks. So
okay, thank you.
To the location data fusion, and I believe this is again Ben Meunier from Brunel University, right? That's. I'm not sure whose screen I was.
Hi.
Yeah.
Sorry.
Okay. Hello, Ben. Yeah. That's
Trouble with the microphone.
Okay. Good. Welcome again back, Ben. Please go ahead.
No worries. Hi. So I'm going to be presenting the location database and the Kalman filter that we used and modeled. So initially, oh, sorry, this is the wrong. Sorry, share the different one. Okay, sorry, let me just get this right. No. Okay, sorry, hi. Sorry about that. Yeah, so just a brief overview. We're going to be taking you through the location database, the kind of modeling process, the Kalman filter and the variables that we used, and then discussing the output and the response from that. So to gain an overview, I know that Lena discussed this as well, but just in a more broad aspect, for the positioning part, we take the millimeter wave time difference of arrival measurements in the uplink channel through the random access network, and we calculate those in our remote radio lighthead controller, as you can see here in the figure. We then perform the VLC receive signal strength measurements in the downlink channel, so the user equipment calculates the position estimates there. Both of these are then transmitted and stored in the location database, which handles most of our system. The location database consists of the anchor points. So these are the priori known locations of all of the antenna coordinates. And now with our updated algorithm, this will also contain the fingerprint data for the VLC side as well. As we said, this also contains the millimeter wave time difference of arrival data and the VLC data, both from the radio lighthead controller and user equipment. Finally, this stores the outputted position estimates, which are calculated by our designated location server. So the location server itself generates the position estimates by drawing in the anchor points, the millimeter wave location data, and the VLC location data. This then utilizes the Kalman filter for our data fusion to provide the position estimates back to our location database. These are then returned to the user equipment and the client for whatever application might be used at the time that requires the position data. So our location server sequence is demonstrated here on the right. As we know, we have the location database tables that we're collecting data from and outputting to. And so it runs through receiving and storing the anchor points. So the first point is the initialization, is to retrieve the anchor point data so that it can perform the calculations. It then receives the latest time difference of time of arrival or time difference of arrival data from the location database, and we perform a check here to check whether this is new and updated data or not. This is done so that we're not processing old and unusable data, or wasting time and processing. So we also do the same check for the VLC data side as well, performing a check here to basically reduce computation. We then, once we know that we've got valuable data sets, perform the time difference arrival process, and then the receive signal strength process, as Lena's just gone through in the previous presentation. And then these two are fused together with a Kalman filter. These updated results are then uploaded to the position estimates table in our database. So one thing that we had to do was we had to model the system, and one of the key constituents was the latency throughout the system. So we calculated the runtime of several components, and here in the lower figure you can see the transmission rate between the radio lighthead controller, the location database, location server, user equipment, and our user display. So you can see the separate timings, and here we have the motion to photon latency. So this is from our user movement all the way to our display, which is delta T8 here at the bottom, is equivalent to the position estimate plus the render and display time. The render and display time is very variable depending on the complex scenario, and we pessimistically assume this to be 12.5 milliseconds. The position estimate here, delta T1 to 5, is a summation of the measurement time, delta T1, which is known to be 2.5 milliseconds as proposed originally by the project. And then the calculation time, so how long it actually takes to estimate the position based on those measurements. All the other latencies other than these were processed through execution runtime, and you can see up here. So overall, we figured that we have a refresh rate of 12.5 milliseconds, which shows in this redundant data sets here, the location server was actually performing not as quickly as we'd hoped, and so we won't be able to perform location data on each single measurement, so we have redundant data sets here. The overall motion to photon latency was estimated to be 29.2 milliseconds from this study. Sensor fusion, for those that don't know, with the Kalman filter, a very robust and well-known system, enables prediction of the user with almost no data at times, and uses the uncertainty and weighting of the uncertainty in noisy measurements, which makes it very, very robust. And it's also not very computationally intensive, which is great. So it obviously consists of two stages: the prediction stage, which uses a physical model to suggest a position, and then an update, which compares the prediction from the prediction stage and the measurements to evaluate an output. So here you can see if we take one of the states that we input at the very beginning, initialization, we perform the prediction using a kinematics model that I'll go into in more detail, but we used a free movement model. This then goes to the update, where we include both our millimeter wave data and then our VLC data. And then this is looped over. And so here you can see the distributions where you might have a prediction, your millimeter wave data set, your VLC data set, and then the weightings and considerations of these are put together to prediction state. Which is essentially to say that your position at time t+1, or your next state, would be equal to your initial position plus your velocity times the difference in time there. Here you can see our state transition matrix, so x equals ax, where bu is 0. So here you can see that our position at x is equal to position x plus delta t times our velocity at x as well. Our Q matrix, or our noise matrix here for our estimate, was estimated, as you can see here, which is generically taken, with our variance of acceleration being 0.3 for our testing that we calculated through runtime.
Ben, are you there?
Ben, yeah, I mean, I think there is.
Ben, you keep cutting out the audio. Ben?
Hello, can you hear me?
You're right now. You're all right now. Yeah, you keep cutting out for some reason.
Oh, I'm very sorry. I'm very sorry. I think it's something to do with the Wi-Fi here. Sorry about that. Do let me know if you lose me again.
Okay.
Where did I miss off?
You were just on the previous slide, and we might have missed a little bit.
Okay. Essentially, here we have our constant velocity model that we implemented into this equation here, x equals ax, where bu was 0 because there was no input. And so you can see the various values we use for our filter prediction. Just try and catch up with lost time. In our update state, we repeated sequentially for both the millimeter wave and the VLC. So we performed it first with one data set and then updated again. We used the Kalman gain equation normally, then updated our state matrix, and then our covariance for that, where Z in these algorithms represents the position estimate that we get from either millimeter wave or VLC, and R represents the respective covariance matrix, so the uncertainty of that measurement. Our VLC values were taken directly from an ISEP received signal strength measurement campaign in a previous study, and you can see the values that we put in for our model here. The millimeter wave R values, however, were taken as the average variance for each axis when we simulated the same environment and we measured points every 10 centimeters in a 3-meter cubed room. This was applying a 0.3 nanosecond time variance to our time of arrival data sets. And so we derived our performance results, our uncertainty for our millimeter wave. Finally, our p-values were initialized as equal to q, and an initial state was given as the user's actual position. So this is something that we need to rerun again. And our delta t value was our refresh rate as we calculated our latency components of 12.5 milliseconds. Overall, we used 5 different scenarios. So we tracked a user doing various things, standing still, watching a YouTube video in Google Maps VR, walking in a circular path, and playing a more active game. Overall, we can see that there's a strong correlation, as expected, between the 2 variables of acceleration and error. This is due to the constant velocity model that we used, and this is a fairly regular occurrence. Overall, though, the average area was about 5 to 12 centimeters between all of the scenarios. So obviously, the worst one being the more active one. We did, however, notice an immediate rise before oscillation or stabilization, which we concluded was due to the filter being used in a dynamic environment and never reaching its steady state. So this is due to it initially relying too strongly on its prediction values. So what we did for a further study was we increased the certainty in our measurement data sets to counteract this, decreasing our R values for both millimeter wave and VLC by an order of 10. What this led to was a large reduction in overall error. So here you can see our data sets for R over 10 in dark blue. And we can see that we now have average errors of 2 to 8.7 centimeters, which was a drastic increase. However, the profiles here that we can see in comparison with the previous study are a lot more irregular. And we notice the standard deviation drastically increases, which shows the trade-off between accuracy and precision from this additional move that we made. And that's due to a too high now reliance on the unstable measurements. Overall, we conclude that the performance of the indoor positioning system throughout our model is impressive for a 5G wireless localization system. This definitely meets the IRL standard of of a below 10 centimeter accuracy and had a very, very low end-to-end latency. We will be conducting further studies to receive a more stable tracking response, however. And we might do this, we're looking at further work in alternative filters, so using adaptive filtering, improving the kinematics model from a constant velocity one, and improving the filter perhaps through the use of particle filters themselves. We're also looking to decrease our measurement error values. We used quite high ones, which were a lot higher than previous studies that we've seen, and possible measurement campaigns might bring to light more realistic values. We will also be looking to reduce the motion to photon latency, which will in turn reduce the error by investigating a more suitable render and display latency, and perhaps running it in a C++ language instead of a Python interpreter, which is known to be slow. And we may be using complementary data from various devices. Thank you very much for listening. I hope I haven't gone over time, and I'll answer any questions. Thank you.
Thank you very much, Ben. There is one message. I don't know whether it's... okay. So just a message to everybody that we will keep the meeting room open, but we will stop recording.
Okay. So no specific questions. Shall I stop sharing?
Yeah. Please. We move on then to the next speaker. The next speaker is Karim Ali, who will be presenting. He's also from Brunel University. He will talk about the Follow Me TV.
Hello, guys. Can you hear me?
Yes, we can hear you, I confirm. And we can see also your screen.
Yep. Today, I'm going to be presenting the smart television services using NFV and SDN network management.
Maybe just a comment. I think we also, again, having a bit of an issue with the voice. I don't know soon whether you can do something centrally, or we can help a little bit. It's a bit.
Can you increase the volume, Karim? Because a little bit, or speak louder.
Yeah, it's partly the volume. It's also a little bit distorted.
Just one second.
Are you right, Karim?
Can you hear me now?
Yes, I can.
Yeah? All right.
That's much better.
Yep, that's perfect. The next generation mobile solution is adopting new access and routing technologies and introducing new solutions incorporating built-in services to improve the quality of experience for users. We're integrating the NFV and the SDN into the home environments so can potentially provide smart television services and improve the quality of experience. The Follow Me service is one of the services that can be addressed through a robust mechanism for switching between multiple 5G radio access technologies and SDN-NFV driven intelligent home IP gateway of the IoRL project. The system architecture of the Follow Me service consists of an end user application installed on the user equipment smartphone, an SDN controller, Follow Me application, which is written in Python, running on top of the SDN controller, and a cache proxy server. The main focus of the Follow Me application is to enable the SDN controller to update the OpenV switch, forwarding tables with the correct TV destination. The Follow Me application utilizes the user equipment location update information to ensure real-time traffic switching instructions to be sent via the SDN controller. The Follow Me service interacts with the network's entity as to realize the service. The service procedure starts with a user registering, requesting a video content. Then the OpenV switch forwards that request to the proxy server, and the proxy server will look and see if this video is cached in. If not, it will go and get it from the internet. Then based on the user selection, the OVS would forward the video to a selected TV set. And if the user changes the location, it will wait for an update of the location to be sent. So it will pause the TV and then the streaming videos until it waits for the new update of the location. As you can see here, that's the layer 2 of the Internet of Radio Light is capable of forwarding Ethernet frames to TV based on tags provided, and will also include the RRLH destination information inside. The connection is established for the Follow Me service and downstreaming of the video. It's all based on the location updates of the user equipment that's already been cached earlier to the system. The proxy splits the sessions into 2 TCP sessions, a user equipment proxy and a proxy content server. The FMA monitors the Follow Me server client's location updates and modifies the OVS, follows the rules when necessary, ensuring that traffic delivery to the correct TV is there. SDN intelligence plays a very important role in improving the performance of the Follow Me service, where the rear controller configures the OVS to select the downstream path, either VLC, millimeter wave, or the Wi-Fi link based on the acquired network. As you can see here, that's the Follow Me application. It's registered as a listener for 2 types of incoming messages: Follow Me request messages and location estimation messages. It asks a new message: is it an initial request? If not, it's a location update. Yes, it looks at the user equipment, it finds it. If not, it ignores the message. If it finds it, it goes and compares the location information to the location that was before. And if it's a new request, it forwards the video request to the proxy server and looks up the user in the lookup. And if the user is found, then it compares it to the earlier cached location. If it's the same room, ignores the message. If it's a new room, it gets the coordinates XY and the TV, IP, and the MAC addresses, and modifies the OVS flow. This is the deployed network topology that we use for multiple room home scenarios. The proxy receives 2 types of messages as well. It's the initial video request and update message. It says URL message. If it's a URL message, it looks for it in the cache. If it's not in the cache, it starts the TCP session and get the content. If it's in the cache, it gets the video and send it to the user. And if the URL message is it's not there, it updates the message instructions, pause the instruction, buffer and pause, or stop the instruction and end the stream. We use two important tools to emulate and generate traffic in our system to test the performance. We use Mininet emulation tool and iPrev traffic generator. As you can see, the deployed network topology in a hypothetical multiple room home scenario. The network consists of an OVS, a Rio controller, and we have 8 hosts to emulate the different network entities. 4 of the 8 hosts emulating our TV sets, as you can see on the left hand side. One of the hosts is registered as a follow me servers client. 2 of the hosts are running in a server client mode, are emulating the location server and a location database. These servers are used to perform client's location estimation and storage mechanism. The last host is running the iPrev traffic generation to emulate the proxy server that is streaming cached videos to the client. On the left-hand side, you can see the stream jitter for the first test scenario ranged around 0.03 milliseconds with some spikes in random times. Although the worst jitter experience was below 0.1 millisecond, this jitter was due to the nature of the iPrev tool. It's worth mentioning, according to Cisco, that the acceptable jitter for this video is below 30 milliseconds, which proves that our system performance is excellent. On the right-hand side, it proves that there was no packet loss within the network during testing. To stitch up all the results together, the figure shows the client random location with respect to the hypothetical home scenario during the test run time spent in each room for each scenario, and the client hoop time. When comparing the hoop times for each run in each scenario, as shown in the figure, with the system performance, it can be clearly shown that there is no performance degradation during handovers whatsoever. For instance, at 41.5 seconds, the client hands over from room 1 to room 2. Thank you very much. If you have any questions, please let me know.
Thank you very much, Karim. I think, yeah, I mean, I still haven't seen any questions or comments to that presentation, neither to any of the previous one. I don't know. I mean, I was very pleased in the beginning of the day. There was a very lively and a lot of discussion happening. It sort of appears to me that maybe our audience is getting a bit, maybe a bit getting exhausted, or but I hope that they are all thinking and formulating questions. So with that note, I would like to invite our last speaker before the lunch break. And this is Harilaos Zarakovitis from the National Center for Scientific Research, Demokritos, who is going to talk about load balancing. And yes, here he comes already. And
yes. Hello, thank you, Adam. This is Harilaos Zarakovitis from the Greek National Center for Scientific Research, Demokritos. I'm going to be presenting two key processes of the IoRL system, namely the traffic load balancing process and the access point assignment process. So we will start with the load balancing process, which is a process to distribute traffic across coexisting networks.
Sorry to disturb you, Haril, sir, but you are not, you are not in the presenter mode. Yeah, I think it is coming now. Yeah.
Sorry about that. Yes. Okay. So yeah. So at this point, we wish to recall that the IoRL system is a hybrid system by means of including the b.VLC, millimeter wave, and Wi-Fi access networks that coexist in a common system. And therefore, the load balancing process is to distribute the traffic across these three coexisting systems. We have implemented this process in the form of a virtual network function and integrated within the SDN-NFV environment of the IoRL system. Actually, considering that this is the macroscopic view of the IoRL system environment separated using layers, the service layer, the NFV and SDN, and the access layer. The load balancing and the access point assignment process take place at the NFV and SDN layer, and more specifically, it takes place at the SDN controller, where the incoming traffic here has to be split within the three networks. So and then a controller at the MAC layer has to again split the traffic in order to assign the user to a specific access point, either Wi-Fi, VLC, or millimeter wave. So the macroscopic view of the load balancing, the flow diagram is depicted in this picture, where we have set two thresholds. We have simulated the load balancing process using the real controller and considering 50 servers and 50 users within the network. So these are the details that have been used during simulations, and this is the results. Well, these three pictures regards the performance of the network without load balancing, and here we can see that the overall traffic is only split within the VLC and millimeter wave networks, while the Wi-Fi network does not have any traffic, does not serve any of the users. While in this video, the overall traffic is split between the VLC millimeter wave and the Wi-Fi networks. So the traffic is indeed splitted. However, this is an empirical, like a programming-like approach, because and not an explicit, because considering that users, considering a room here with many remote radio light heads, I mean, VLC millimeter wave and a Wi-Fi access point at the center of the room, and considering that these users change position and also change their quality of service requirements, a key question is that how to decide which access point is most suitable, the optimal access point to be assigned to its user, considering its user's positioning and quality of service requirements. So here comes the access point assignment process to answer this question. And this process is a process to distribute the traffic across coexisting access points, not only networks, like it happened with the load balancing. So why to consider? Because in the Internet of Radio Light VLC millimeter wave access points can cover relatively small areas of approximately 2 or 3 meters diameter, while the Wi-Fi has ubiquitous access. For example, in this figure, we see that a user can be within the active zone of a VLC lighthead. However, it can be some random time instances while this user moves across the room. It can be placed within a dead zone where no millimeter wave or VLC access is available. And thereby, this is however, on the other hand, the Wi-Fi has ubiquitous access, but it has less network capacity. And therefore, the main problem here is to balance the coverage versus capacity of the IoRL system, considering all the users and their requirements and position. So the access point assignment we studied is to cover this trade-off, coverage versus capacity, by associating the users located into dead zones with the Wi-Fi access points, while keeping the rest of the users connected to the b.VLC and Meunier networks, and by considering a minimum quality of service requirements of these users by means of throughputs, the quality of service throughputs. Also, we have implemented this process in the form of BNF, and we have produced 3 publications. The first is at the IEEE Transactions of Wireless Communications, the second on the IEEE WUT conference, and the third at the IEEE ICC conference, which is also relatively recent. So at this slide, what we are presenting the novelties of this approach, of the access point and load balancing approach. So this is a previous picture where depicts the conventional way of implementing load balancing and access point assignment. So the load balancing takes place at the network layer in order to split the traffic between networks, and then the access point assignment takes place at the MAC layer in order to split the traffic between access points. However, what we did is that we leveraged the intensive computation that takes place at the MAC layer. So we leverage the computation of this controller here by moving these, let's say, tasks at the controller at the network layer, where traditionally at these controllers have more capacity than controllers used at the MAC layer, I mean layer 2 or layer 3. Also, we somehow depict the main optimization problem with the main constraints of with these 3 main constraints. So the optimization objective is to maximize the throughput subject to the class of the users, subject to the minimum quality of service requirement by means of throughput, and by assigning 1 user to each access point. And these are the constraints that the main constraints. Of course, there are other that are not presented in order to make the presentation easier. And this function is the data array that has been considered, and we depict it because we wish to show that this parameter here, the access point, the assignment, the access point indexing, which is a 3-dimensional variable. And that makes this approach novel, because until now there are traditional ways. These problems were traditionally formulated by means of 1-dimensional, or there are 2 studies that have approached this by means of 2-dimensional access point assignment indexing. So we approach it by means of a 3-dimensional variable, which requires fundamentally different way of resolving it. And not only that, here we show the result in order to show that that this result is independent of iterative mechanism, right? And also we resolved it using the standard Lagrangian convex optimization analysis, and not using dual Lagrangian optimization analysis. That means that we avoided the issues that are issued by the duality principle, like the duality gap convergence of the algorithm. And this has major impact on the implementation, on the complexity of the algorithm. So the novelties, to sum up the novelties, is that we leverage this capacity, the capacity from the MAC layer to the network layer, and that we formulated this project and resolved it in a very efficient way. Also, another note here, I feel that it is important to say, is that this problem can be expanded by means of including the energy efficiency instead of including only the throughput, or even include the delay instead of including only the throughput. So this is flexible to be, or even include, or even consider that not only 1 user is assigned to 1 access point, but more users can be assigned to 1 access point, which we have attended it, and it also relaxes somehow the solution of the project. So this is a flexible problem to be to consider, for example, energy efficiency or other parameters, and also implemented in the form of BNF, which means that it can be implemented to other systems, not only the IoRL system. So during our simulations, here at this point here, we got the conventional, let's say, approach that it is extracted by these two papers mentioned previously, and this is our approach. At the conventional approach, we see that there are three different classes of users. The class 1 has high quality of service requirement, class 2 medium, and class 3 low quality of service requirement. However, we see that class 1, this is a random time instance, but we see that this user 20, is assigned to the Wi-Fi. These two are the b.VLC and millimeter wave access points. So there is no association between this highly demanded user with b.VLC and millimeter wave, meaning that this user is not serviced adequately. And also for these two class 2 users, it's no association with b.VLC or millimeter wave access points. However, with our approach, by taking exactly the same coordinates here and positioning of the users and quality of service requirements, all class 1 and class 2 users, the highly demanded users, are assigned to the b.VLC and millimeter wave beams, while the class 3 users, which have lower priority, are assigned to the Wi-Fi. So the result, as said previously, we are looking for a throughput versus fairness trade-off, right? Capacity. So we see that in the conventional approach, the throughput is higher, while in our approach, the throughput is lower. However, the fairness index at this point is much higher than the conventional approach, which means that users get at least their minimum quality of service requirements. So we achieve a maximization of the trade-off between throughput versus fairness compared to traditional approach. And also another observation is the implementation time of this algorithm, which is sufficiently low. We see here that the number of iterations and the iteration time needed to implement this algorithm, because as said previously, it is independent by it is a straightforward formula, right? The solution is given by means of a straightforward final formula. So we achieve greater throughput versus fairness. That means that all users, all users are getting serviced with a very in a very fast way. And that's all from my side. If any questions, please feel free to ask.
Thank you very much, Harilaus.
Thank you.
And indeed, there was a question. Meanwhile, I'm not 100% it's for you. I mean, it could be for you, or it could be also maybe within, because there were also some other load balancing discussions earlier. So the question is, what is the most efficient algorithm for the load balancing in the VLC and millimeter wave networks? Or also maybe in between the two types of delivery?
Sorry, is this question for me?
Well, it could be to you or to the whole group. So the question is, what is the most efficient algorithm for the load balancing in the VLC and millimeter wave networks?
Yeah. Well, as far as I know, to the best of my knowledge, there is no taxonomy, if I'm not mistaken. I mean, there is no standardized way of distinguishing algorithms to be used in load balancing. We use algorithms that are, let's say, somehow custom by means of, like I saw previously, that we wish to increase the throughput or the energy efficiency or minimize power. So accordingly, we design the algorithms. If this is the question, I feel that, however, I don't feel that there is a standardized way of distinguishing algorithms, of naming algorithms to be used in load balancing or access point.
Yeah, so sorry, maybe yeah, I mean, the question is about which is the most efficient, right? So I don't know whether regarding efficiency we can comment, can we rank them regarding efficiency? Again, I'm not even sure how it is defined, the efficiency of a load balancing algorithm.
The efficiency can be defined by means of the incoming traffic to be the summation between the traffic over the coexisting network should be equal to the incoming traffic. This is the first thing. That means that no traffic is wasted, right? That no resources are wasted. This is the first thing. And the second one is the complexity by means of how fast the algorithm can decide where to redirect or direct the traffic. So I feel that these two criteria are the most important in order to somehow highlight the performance of a load balancing algorithm or an access point assignment algorithm, and in general in decision making. Right?
Okay, I mean, in case we did not manage to answer the question right away orally, I mean, please come back to us and then we will try to then provide a written answer. So thanks again, once again, Harry Laus. I mean, this basically concludes the morning session.